All right. Welcome back. You guys probably forgot everything. I think this is, I really don't like this, the whole week away and then you come back we have 2 weeks, right? We get to meet here 6 more times, or 5 more times after today, and then we have an exam, right? I've checked out. Have you guys checked out? I mean, you're gone for a week. Like, I don't like this. I'm going to complain. I heard, I wasn't teaching at the time, but I guess, was it last year? You guys ended at Thanksgiving, right? Yeah. That seems legit. Right? You do have to start a little earlier in the summer, but that's not that bad.
6 weeks off. 2 weeks off.
What's that?
They cut 2 weeks off of the semester.
Yeah, see, that'd be sick. Let's do that, huh? So anyway, luckily for us, we ended indeterminate beams, right? Deflections of determinate, indeterminate beams on Friday. Not on Friday. We didn't have class on Friday, but Wednesday before our little week break, okay? So that ended deflections, and now we're going to start pressure vessels. And then we have one more, what I would consider part 2 of combined loading, where we're going to take everything that we've learned and put it all together, right? Now we've got beam bending, we've got axial loads, we've got torsional loads, we're going to have pressure loads. We can put all of those things onto elements, because in the real world, that's what really happens, right? We've got a lot of different load sources acting on elements. And so we got to look at each of those load sources and see what their contributions are, add them all together, and then look back at our allowable capacities, right, to make our design efficient and effective, okay? So this week, hopefully pressure vessels. Next week, combined loading. Week after that, we have one final. We're going to be in here, I think it's Wednesday at noon to 2. Is that right? Yeah.
How long is the syllabus?
We're here for 2 hours.
2 hours?
We're here for 2 hours.
Do we get like a review or anything?
Yeah, we can. I'm hoping that the Friday before finals week, we'll have some time. I think we will have some time. Okay. Bring questions, I guess, on that Friday, next Friday. Okay, bring questions.
Maybe 2 on the 15th.
Am I writing it? Yes, I'm writing it.
So like you know it's going to be on it. Right?
Yeah, I mean, eventually. I haven't written it yet.
You should solve some of those.
Yeah. I know that I've split it in half, okay? There's half of it is going to be conceptual, pretty much multiple choice, okay? Sort of questions. And then the second half is going to be kind of the more longhand questions, which obviously I'm not going to be, well, you might consider me an asshole about it, but I'm not going to go back too far, okay? You might think that I went back too far, but like combined loading, that essentially takes everything that you guys have learned in this class and brings it all together, right? We have torsional stresses, we have shear stresses, bending stresses, axial stresses, all of those things, and we're going to touch on those things next week. And so hopefully that'll be a nice review to bring everything together. Yes?
What like percent of like total points is it worth?
It's worth 20%. Yeah, 20%. So a lot.
If there's 50 multiple choice questions, how many word problems are you putting in?
Yeah.
Probably like 3 or 4, something like that, maybe. I don't know. Let me get closer to building the damn thing, and then we'll talk about it, okay? Are you scared about it? Yeah. Whoa, hold on. What'd you say? Yes. You'll get a cheat, basically. I'm going to let you bring in a lot of things, okay? I'll tell you what those are next week, but you'll get to make up your own cheat sheet. You put whatever the hell you want on it. I'm going to let you bring in all of those note sheets that were like 0, 0, 0, 0, 0, 0, like the appendix, the shear and moment diagrams, the deflections of beams, what else? The text does a very good job, and like one of the lecture notes that I put out on D2L is essentially a recap of all like the major equations in every chapter for the whole book. You can bring those in. Okay. I'm excited for this, and it makes me feel so good that I'm past that, you know. But you guys will be past it sometime too. Okay. It's so, yeah.
So you're taking this
I've taken a lot of tests in my day. Yes.
You saying
somewhat. Me versus you, okay? Wednesday, December, whatever the hell it is, 15th. Be here. 12 o'clock. I think it's noon. Well, we'll hammer that out later too, okay? Don't be too scared, okay? It's just your future. All right? So let's talk about pressure vessels. I like pressure vessels. They're very simple. They're pretty easy. We're going to derive some equations, okay? Very common things, right? Everybody, I think, has seen a propane cylinder, 20-pound propane cylinder, like the 1-pound propane cylinder, little green Coleman's, okay? That'd be considered a pressure vessel. We've got pipelines, we've got fuselage for aircraft, right? Those are a pressure vessel. When we go up to 35,000 feet, right, the pressure outside the cabin of the aircraft is a lot less than the actual cabin inside. Okay, they try and make it, I think they equalize it somewhere around 10,000 feet for us, okay? So that our ears aren't going crazy and things like that. And then the little pressure cooker. What the hell are those things called again? Instapot. Anybody have an Instapot? Beautiful invention, right? Or reinvention of the original. I remember growing up, my mom had like one of those old school, maybe your parents did too, old school like big ass metal thing. And it just had this little weight that set on the top of it. And the weight of the lid essentially kept it, and so it elevated the pressure. You cook things faster, right? Elevated pressure means elevated boiling points, which means you can raise the temperature to cook things faster. If you don't have an Instapot, this is my recommendation to get an Instapot, okay?
They're expensive.
Are they?
No, I got one from the thrift store for $12.
See, 12 bucks. You can handle 12 bucks.
I throw
Friday sales of pressure cookers and air fryers. They were all like
Air fryers?
Oh, air fryers?
I've heard those are legit too.
That's your next purchase.
Okay, deal. Writing that down. Air fryer.
Air fryer.
Okay. So it holds fluids such as liquids and gases that may be stored at relatively high pressures. Okay. There's two big designations with pressure vessels. There's pressure vessels we would call thin-walled, and there's pressure vessels we would call thick-walled. Okay. When the inside radius is greater than 10 times the thickness, we're going to call it thin-walled. Okay? R sub I, inside radius, and T is what we would call our wall thickness. So, I mean, if we had a half or a 1 inch thick pressure vessel, right, the vessel itself would only really need to have a radius of 10 inches to be considered thin wall, right, which isn't that hard. If you think of like a basketball or something like that, that's definitely a thin walled pressure vessel, right? Volleyball, soccer ball, all of those things. What's special about thin walled is that our normal stresses is relatively uniform. So our maximum sigma, maximum normal stress, is really less than or equal to 5% greater than the average stress, or average normal stress. This is really nice, right? So we don't have to worry about bending. It's really what we're trying to get away from, or we get away from when we start looking at thin wall pressure vessels, that it's so thin that it acts as a shell. Call them shell structures, membrane structures. And luckily for you, that's what we're going to focus on in this class, okay? gets to thick-walled, then you get weird differential stresses that act in the walls of our pressure vessel because it's so thick. But as you can imagine, right, if it's 1 inch thick, I mean, that's pretty thick-walled. It only really needs to be 20 inches in diameter before it becomes a thin-walled vessel, right? So if we start by looking at, we're going to look at a couple different types of vessels. One would be a spherical vessel, and the other one is a cylindrical vessel.
Quick question.
Yes.
If the inside radius is equal to 10 times the thickness, is it also thin walled or would it be thick at that point?
I'd call it a thin thick. Right at the edge there.
Thank you.
I mean, I would probably consider it thin wall just because it'd make my life a lot easier. Okay.
That's fair.
We won't be right on that line. You won't have to make that call. Okay. It'll be very, very straightforward. Okay. So, as with anything that we've done in this class, we've done a lot of free body diagrams, right? So in order to understand the stresses, which as engineers, we really are interested in what's going on in the walls of this sphere, right? Soccer ball, basketball, or whatever it is, cylindrical, a lot of like refineries, like natural gas refineries and stuff have big cylindrical tanks, or spherical tanks, sorry. And so if we do a free body diagram of the sphere vessel, right, and it is under pressure, right? So we have a typical sphere, soccer ball, okay? Put a little pump on it, pump this soccer ball up, right? It's got some PSI in it, some pressure inside of it, okay? If we were to cut this sphere in half, so we have 2 half spheres, okay, and we were to draw a free body diagram of that, that's what we would see, right? We would see some sort of stress, we call it a tangential stress, sigma T, in the shell of our soccer ball, for instance, okay? And then the pressure itself that's acting on the inside face of our soccer ball, right? So some force P, and that force P, as we know, with normal stress, force is stress times an area. So this force P that's acting on the internal area of this soccer ball is going to be the stress or pressure. That's pressure we're going to call P times the area, right? Pi r squared, or pi over 4 times d squared. So pi r squared. And this would be our force due to internal pressure. That's our big capital P. That's the force due to pumping up the soccer ball. Well, the soccer ball, in order to hold that pressure inside, right, have a higher internal pressure than our atmospheric pressure outside, that soccer ball fabric or shell has to resist this internal force, right? And it resists it through stress in the shell of the soccer ball itself. Call this the resisting force in vessel wall. I'm going to denote that as R, right? Resisting force R, applied force P. P is from the pressure. Resisting force is from the wall of the vessel itself, right? In this case, we're going to assume a soccer ball. Well, that resisting force, again, is stress times an area. It's the definition of normal stress is force over an area, so we can rearrange that equation. We get force is stress times an area. In this case, the stress that we're going to see in the surface of our soccer ball, we're going to call it sigma T, or the tangential stress. Right? It's going to be acting. If we were to cut this, say sliver this back and cut it right here, is going to be normal to that face and tangent to the perimeter of our sphere. And so that's why we call it sigma t. So it's going to be sigma t times the area. Well, the area that our shell inhabits across this cross-section is really the circumference times the thickness. That would be the area of our soccer ball, right, that we cut through. So we have our circumference in terms of radius, 2 pi r, or pi d in terms of diameter, times our thickness of the fabric of the soccer ball or steel tank or whatever it might be. Well, we're really interested in what is this tangential stress, right? This is the material we're selecting. This is what we're really designing as the vessel itself. We're going to have some idea of a material that we want to use. That material is going to allow us to decide, okay, what factor of safety do we want to impose upon that material? And then on top of that, if we know the factor of safety and we know the material we're using, then we can impose a allowable stress that we can have for, say, this sigma t, right? So sigma t, or tangential stress, can't exceed that allowable stress. So we want to solve for that. Well, we have a free body diagram here, and we know that this thing isn't moving anywhere. So if we're going to sum the forces in the x direction, right, or along this or normal to this section, it has to equal 0. Right? The force in the shell or our soccer ball has to equal the force of the pressure exerted inside the surface of the soccer ball. So we're going to do sum of the forces equals 0. We know that our resistant force, or the force in the soccer ball shell, is our sigma t, 2 pi r times t. It's acting in the positive x direction, right? This is our coordinate system here, positive x direction. Our force due to the internal pressure is acting in the opposite direction, so we're going to call that negative. That big P, we decided, right, was the pressure we put in the soccer ball times the area over which it acts, which is really just the area of this circle, right, the green circle there. So we have minus little p pi r squared. Well, as I mentioned, we really are interested in this tangential stress, or what's the stress in the material of our vessel. We end up getting a PR over 2T, or if you wanted to do it in terms of diameter, P times the diameter over 4 times the thickness. So if you know pressure, you know the radius or diameter of your vessel, and you know the thickness of the wall, you can figure out what stress is in the wall of our vessel. Big P is the total force that's being exerted on the half of the soccer ball. Right? Cut the ball in half. Right? This force, big P, is what's trying to, essentially if you had a soccer ball in your hands, it's what's trying to tear the soccer ball in half. Right? And what's resisting the soccer ball tearing in half is all of the stress that's in that soccer ball, the surface of the soccer ball, the actual material of the ball, right? That's resisting. That's all the little red arrows. So the big P is going to be our pressure, right? 12 psi or 10 psi or whatever you want. Would you use soccer ball? 10 psi? It seems like a lot. What's a football? Come on, Trey. Jeez. Man. You just know you can catch it, right? P times pi times radius squared, right? So pressure times the area. You have 10 psi in here. 10 psi is acting everywhere, cutting that soccer ball in half. So the area that 10 pounds per square inch is acting is essentially the area of the soccer ball, the circle. So you put those equal to each other, and we can figure out, in terms of the pressure that's in the ball, the radius or diameter of the ball, and the thickness, the material of the ball, we can figure out what the stress is in the material of the ball. Sigma T. Something to note here. As with our definition of thin-walled versus thick-walled, we use the inside diameter. Again, we use the inside diameter here. That is the diameter to the initial surface of the ball on the inside. Okay? We had we're going to the inside surface of our sphere. So, if we step a little bit further and look at what's happening, not only tangentially, but what's happening on the three-dimensional surfaces of our sphere, or our soccer ball. Okay, and we looked at a point that was on the inside surface and then the outside surface of our soccer ball. So the inside of the fabric of the soccer ball and the outside of the fabric of the soccer ball. And we were looking at what are the forces or stresses on a block, a little block that we would tear out of the soccer ball and look at. Well, if we look at the inner surface first, if we look at the inner surface, a little square that's sitting right on the inside surface of our soccer ball, we now decided that our tangential stress, sigma t, is PR over 2t. Well, if we cut the soccer ball this way, we're going to get the same stress, PR over 2t. If you cut the soccer ball at a 45-degree angle, you're going to get PR over 2t. Every angle that's in the surface of our soccer ball has the same tangential stress in it. We would call that an in-plane stress, right? In the surface or fabric of our soccer ball, it's going to be PR over 2t, no matter where we cut it. Make sense? Everyone kind of follow that? In the out-of-plane direction, if we're looking at the inner surface of our soccer ball, well, we know that there is pressure in this soccer ball, so that pressure is acting on all the internal surfaces of the soccer ball. So if we look at a cube in plane, on these four sides, we're going to have PR over 2t. Out of plane, if we're looking on the inner surface, we're going to get the pressure, P, small p. That's going to be acting on the inside surface. If we look on the outside surface, on the outside surface, we would call this radial stress. Stress that's acting from the center of the soccer ball or sphere outward. And inside is going to have the pressure acting on it. It's going to be the inside face of our soccer ball. If you look on the outside of our soccer ball, the atmosphere side, the side we see, we're going to have zero radial stress, There's nothing acting on the outside of the soccer ball, was just sitting there. Okay? So we kind of have these two stress states of what's going on in plane and out of plane, both on the inside surface and the outside surface of our vessel. The tangential or the in-plane stresses is always the same, whether you're on the inside surface or the outside surface, we still have PR over 2t. It's that out of plane or radial stress that's acting in the direction of the center outward, that's going to change depending on what surface you're on. Well, as we know from beam bending, changes in normal stress, changes in moment, which is changes in normal stress, result in shear stresses. Okay? So we have normal stresses. You can say that we have normal stresses now. Have normal stresses. That was easy. We just cut the ball in half. But what is our maximum shear stress? And we have our two locations of interest. We have a location that's the inside surface of our ball, and the outside surface of the ball, right? We have inner surface, outer surface, well, as we just discussed, right, established, we have out-of-plane stresses and in-plane stresses. Our in-plane stresses are the stresses that are in the plane of the ball or in the material of the ball, right, the tangential stresses. And then our out-of-plane stresses are the stresses that are acting radially, right, going inside and outside of the surface of the ball, which change depending if you're looking at the inner surface or the outer surface. So if we look at out-of-plane, versus in plane. If we look at out of plane, we have this variation of stress between our two locations of interest. Out of plane means we're looking at our radial stresses. Well, our radial stresses change from inner surface to outer surface, right? Inner surface, we have the pressure. Outer surface, we have zero. So we have a stress variation. From PR over 2T to 0 or to P, right? We're gonna start looking at more circle here, okay? If we remember our stress blocks, which were our little squares. So we're going to have an in-plane stress block, right? That's essentially cutting this cube in line with these four stresses. And we have an out-of-plane stress block, right? That'd be cutting it kind of in and out of the page here, where we have our radial stress on two surfaces and our tangential stress on the other two surfaces, right? And as you know from Moore's circle, right, the variation in those stresses on those two faces is what makes us, or creates the ability to have this circle, right? And the bigger the circle, the bigger our shear stress is, right? Our shear stress is the radius of our circle. So if we have stress variation from one side of our stress block, right, if we looked at a stress block, we're going to look at PR over 2T. And this is going to be 0 to P, right? So we're going to have a stress block where we're going to have our tangential stress, doesn't change. But this radial stress is going to change, right? So we have two stress states. So therefore, we have shear stress, right? We have tau, because we have variation in normal stress. If we look at in plane, right? If we look at an in plane block, as I mentioned, we're going to cut. If we look at a block that's cut in plane, we're going to cut it along this surface right here. So we have PR over 2T acting in both directions. So we've got our stress state, right? That looks something like this with PR over 2T acting on all four surfaces. Our stress state, based on our free body diagram here, right? There's no shear stresses currently in the stress state that we're showing. But as we know, Moore's circle, it's a transformation of stresses, right? If you were to start rotating this cube and looking at stresses at all different angles, you're going to establish shear stresses. But if you look at in-plane stresses, we're going to get zero, or this essentially becomes a point on Moore's circle. I'll show it to you. Become more apparent here, but Moore's circle is just a point, right? We plot our x faces and our y faces on Moore's circle. So we have 2 points to plot on Moore's circle. In this case, right, we're going to have a normal stress and a shear stress. Shear stress is 0. So we have a normal stress of PR over 2T. In the other direction, we've got this, we're either going to plot 0 and 0, or the pressure and 0. Right, so we've got 2 points on our Moore's circle. Well, if we plot our x face and our y face, our stresses are the exact same. We're essentially going to plot 2 points right on top of each other. We can't make a circle out of that, right? It just becomes a point on Moore's circle. So if we draw a couple, knowing that, and we do our inner surface. We look at our inner surface and our outer surface. On our inner surface, right, we've got 2 stress states. We've got our out of plane and our in plane. Well, if we look at our out of plane, we're going to have this stress of PR over 2T and 0 shear stress. And then we're going to have a point over here that's negative P, right? That's our inner surface. It's going to have the pressure and 0 shear stress. Essentially plotting these 2 points. And then if we were to create more circle, right, the radius of our circle is our maximum shear stress. So if we look at tau max, and honestly this should be the other way. This should be compressive, right? If we have, so switch those arrows around. If we have pressure in our soccer ball, right, the air pressure is going to be pushing on the surface of the inner surface of our soccer ball. So it's going to be towards the surface, which would mean that it's in compression. If it's in compression, it's negative, and that's why this point lands out here. Well, we know our maximum shear stress is the radius of our circle. It's essentially the average. So we've got sigma t minus sigma radial equals 1/2. We know our tangential stress is always PR over 2T minus, in this case, we've got this stress acting radially on the inner surface, which is the pressure that's in the ball. And we end up with tau max equal to PR over 4T plus pressure over 2, P over 2. That's what this is, right? So that's what they got. That's how we got there. Essentially figuring out the radius. So that's looking at a circle at the inner surface, right? Moore's circle, where we plotted both the out of plane and the in plane stress states. The out of plane, we're looking at the inner surface. We got this stress block with the pressure acting. So we got this point, which would be plotting the y. This point, which is plotting the x stresses, right? 0 shear stress. We have a normal stress, PR over 2T. We construct our circle. We also can plot the in-plane stress state, right? Which is going to look just like this. that stress doesn't change. As we mentioned, we're going to plot both the x face and the y face stresses on our Mohr's circle. Those are the exact same, right? The in-plane Mohr's circle is simply a point. We're going to plot both those points and they're going to land in the exact same spot. Okay? We do that exact same exercise for the outer surface. We get a sigma max or a tau max of PR over 4T. That's essentially the radius. Well, now we're plotting our other stress state, right? On the outside of the surface, at the outside surface, our normal stress on, say, our y face of our stress block is 0. So we plot that. And that's our y face, 0, 0, 0 shear stress, 0 normal stress. The other side of our stress state, we have our tangential stress and 0 shear stress, right? That's our x face of our stress block. We plot that, goes over here. Try and find the radius of our circle. Radius of our circle is essentially the maximum, which is PR over 2T over 2. That gives us our radius, which gives us our maximum shear stress. And out of these two, right, as we find out, our shear stress is ultimately maximum at the inner surface. And that's due to having internal stresses acting on the wall of the vessel. Right, so inner, larger, due to internal stress acting on wall of vessel. Don't see any tears yet, so we're good. Okay. We're going to talk about strain because the possibilities of you guys dealing with this is very slim. I'm just going to give it to you. Okay. If we looked at the strain at the outer surface of our ball, you can find all of this in chapter 13 of the text. We can get the tangential strain in the soccer ball or the steel tank or whatever it is. And we can develop an equation for that. It is 1 over the modulus of elasticity times the tangential stress minus Poisson's ratio times the tangential stress, which is essentially equal to 1 over modulus of elasticity. Tangential stress we know for a sphere is PR over 2T. So we can substitute that in. And we finally land with an equation for the strain that's in the tangential direction. It's PR over 2T times the modulus of elasticity times 1 minus Poisson's ratio. And has been, as we have done in the past, it's Hooke's law that helps us establish this relationship. A few other things, okay? But just more than anything, something to have somewhere that if you ever ran into it, you could figure out how far that soccer ball, fabric of the soccer ball stretches based on putting 10 psi in it, based on putting 20 psi in it, right? Based on the diameter or radius, inside radius of our soccer ball, Poisson's ratio of the material, and so on, okay? Questions there? I know it was a lot coming back from a week and a little, right? The problems are relatively simple though, okay? once we know that the tangential stress is PR over 2T, and we have some equations for our shear stress, knowing that our shear stress changes, right? The maximum shear stress is dependent on what surface we're on, whether we're on the inside surface or the outside surface, okay? And knowing that the inner surface is really the larger one, so we're looking at ultimately the ultimate maximum shear stress that the material sees, right? We're going to look at it at the inner surface, and we've got an equation, right? So those are the two big things that we're looking for, shear stress and normal stress, right? So we're going to start an example. Maybe we'll get through it. I think we will. A spherical gas storage tank, as I mentioned, petrochemical plants, especially natural gas plants. A lot of times they'll store gases in spherical containers, and you will know when we get to cylindrical pressure vessels. It's because a lot of times it has to do with the stresses are different, right? Pretty efficient structure being a sphere, okay? So we have spherical gas storage tanks, inside diameter of which are 21 feet, okay? They're constructed to hold gas at 160 psi. We've decided that we're going to construct it out of steel. The steel has a yield strength of 50 ksi. We, kind of scaredy cats, we want to put a factor of safety of 3 on it so we can sleep at night, okay? With respect to this yield strength of 50 ksi. And they want us to determine what's the minimum wall thickness required for the spherical tank, okay? Based on the normal stress. Well, we know the stress in our tank, our normal stress in our tank. For a spherical tank is PR over 2T, derived that. We also know that our allowable normal stress is really what we're going to be after, right? And that is our maximum normal stress divided by some factor of safety, right? We're going to reduce the capacity of the material based on our comfort with what we're using it for. A lot of times this comes from codes and things like that, as we've talked. And in this case, it was given to us. We were told that we're going to be using 50 ksi steel, right? Maybe A572 plate or something like that. So we have 50 ksi. We're going to divide that by 3. So we're going to say that we're really only going to allow this spherical tank to have a normal stress of 16.67 ksi. So you can imagine pretty straightforward from here. We're really looking for the thickness. They gave us the diameter. We can get the radius, and then we also know the pressure. So let's plug all that in, right? So if we know stress is PR over 2T, P times D over 2 over 2T. Well, if we solve for T, we know the thickness is PD over 4 times the stress, right? If we rearrange this equation here, saying that the stress, tangential stress or normal stress in our spherical tank is P times D over 2 over 2T. We rearrange that for T. We get this equation that thickness is the pressure times the diameter, inside diameter, over 4 times the allowable stress. So if we run that, we've got 160 psi. We have a tank that's 21 feet in diameter. Well, psi and feet don't seem like they are equivalent, so I am going to convert my diameter into inches or multiply it by 12. 4 now times our allowable stress is 16.67 ksi. Right, well, we have psi and ksi. So we need to convert one. Well, I'm going to times our 16.67 ksi into psi or multiply it by 1,000 pounds per kip. Right? our minimum thickness of our steel tank that's going to be carrying 160 psi gas, 0.6 inches. Is this thing thin-walled? That's always a good question to ask. Well, if we take 21 feet times 12 inches per foot divided by 2, that's going to give us our radius. Inside radius, that is 126 inches. If we divide that by 0.6 inches, we end up with 210. That's way, way greater than 10. Therefore, thin-walled, and our assumptions that we made with respect to having this nice uniform internal stress, right? Tangential stress is accurate. Super accurate, right? We're at 210. So it's thin-walled, minimum thickness is 0.6, right? Probably use 5/8 inch steel plate of a yield with a yield strength of 50 KSI. And it's as easy as that, right? That's spherical tanks, spherical vessels. I don't want any of you passing out, so we're going to end a little early today, okay? And we'll start with cylindrical pressure vessels on Wednesday. Don't forget, you have homework due by the end of Friday, right? The 3rd. The quiz, that's homework 9. Quiz 9 opens up noon on Thursday or on Friday, and it's due by the end of day Sunday, the 5th. Okay. This is homework in quiz 9. This is the second to last homework and quiz you will have. Good luck. Yeah.